Assalamualaikum. Okay, we start our class by reciting Surah Al-Fatihah first. Okay, amin, amin, ya Rabbal Alamin. Okay. So, I will start with the learning outcome for this chapter. So, in this chapter, you should be able to define the following term, which is fixed law, molecular diffusion, mass transfer coefficient, and interface mass transfer. Okay, next, you should be able to explain the application of fixed law. Compare and contrast molecular diffusion in gas, liquid, and also solid. Next, you should be able to determine the flux or diffusivity of substance in gas, liquid, and solid. Okay, next, define and calculate the convective mass transfer of substance. And the last one, you should be able to explain the interface mass transfer and calculate the flux and concentration of substance at this interface layer. Okay, for this chapter, we have 6 small subtopics. The first one is introduction to mass transfer. Second, fixed law and molecular diffusion. Third, diffusion through stagnant film and equimolar counter diffusion. Next, you will learn molecular diffusion in gas, liquid, and solid. Fifth, convective mass transfer and mass transfer coefficient. And the last one, you will learn interface mass transfer. Okay, what is mass transfer? Where is mass transfer came from? Okay, so I will illustrate to you where mass transfer come from. Okay, in a chemical process, okay, we will have raw material. Sorry, my handwriting is not so because I'm using the pen tablet. It's okay as long as you all can understand, right? Okay, you will have a raw material where the raw material will undergo physical changes. Then it will go chemical changes. Then after that you will get your product. Okay, from raw material you get your product, but your raw material have to undergo physical changes and also chemical changes. Okay, for physical changes, there is unit of operations. Okay, for the chemical, Okay, for the chemical changes, there will be unit process. Okay, so under unit operation, we will have first we call as fluid mechanic. Next is heat transfer. You will also learn heat transfer this semester, right? Okay, so the third one is the mass transfer. Yeah, here you go. Where mass transfer came from. So this one that we will learn in this separation. Okay, for unit process in chemical changes, so it's simple. For example, nitration process or halogenation. But we will not focus on this, we'll only focus on mass transfer. Okay, for these three, there is a need for driving force. Okay, what is driving force? Okay, it's actually simple. Okay, for heat transfer, you will need, for example, you have point 1 to point 2. Uh, the temperature for this, for both the points should be different so that heat transfer will occur. If temperature here 50 and temperature here 50, so there is no heat transfer happen. Okay, so the temperature must be different, so then heat transfer will occur. Okay, the same for mass transfer, there should be a difference of concentration. Okay, so concentration at point 1 and point 2 should be different, then mass transfer will occur. If concentration for both points is the same, so no mass transfer occur. Okay, so without driving force, which is different of temperature and different of concentration, the material will not flow. Okay, so I hope you understand where is mass transfer came from. Okay, so introduction to mass transfer. Okay, what is mass transfer? So here is the definition. So the question for definition of mass transfer is quite popular during exam, tests. So you should be able to understand the definition so that when you understand, you will straightly memorize. Okay, so mass transfer is a net movement. Movement means something is moved from point 1 to point 2. As we say, transfer. So transfer means there is a movement, net movement. Then movement of what? What is moving? Okay, the component, net movement of a component in a mixture. So what is moving? Component in a mixture. Okay, then what is moving? So where it move? It move from one location to another location, where the component exists at different concentrations. So please remember, mass transfer will happen when there is a difference in concentration for point 1 and point 2. Okay, now to make our class become more fun, so I hope you all can interact with me. So we will have a more fun class. Not only me to teach, but you all also can give feedback. Okay, now I will give around 1 to 2 minutes for all of you. Please give me example of mass transfer process around you. One example is okay. If you can give more, so it's good. So I will pick around 5 people randomly to give me the answer. Okay, so you can Google the answer. It's okay. I just want your effort to interact and give the answer so that you can understand more. Okay. Okay. So you all hear, right, what I am talking?
Yes,
Yes.
madam.
Okay, so
Yes.
I give
Why?
you 1 to 2 minutes. You can think, or you just Google the answer. It's okay. Okay, we start back our class. So, I will ask the first person, Siti Nur Hafifa. Can you give me some example of mass transfer process?
Yes, madam. Here I am.
Yeah,
So one of the example is evaporation of water from pond a pond to the atmosphere.
yes. That is one of the example. Thank you, Hafifa. Okay. Next person is Syakir Naufal.
Yes, madam.
Okay.
I found the the pru- pu- the purification of blood in kidneys and liver. I don't know, madam. Macam
Okay. It's okay because you have first time learning. It's okay.
uh,
Thank you for your try, Syakir.
okay.
Okay, next. Putri Nur Shakila. It's okay, don't be afraid. There is no wrong or correct answer. I just want your feedback.
Um, it's evaporation of water from a pond to the atmosphere.
Okay. So we have okay, it's okay. So next, Siti Farhana.
Um, Sugar in coffee.
Yeah, that's right. Thank you, Farhana. Okay, last one. Wan Arif Ruzaini.
Yes, I.
Uh-huh.
Movement of water from aquarium to a bucket.
Okay. When there is movement, there is heat transfer, mass transfer. Okay, thank you, Arif. So we continue back. Okay. Introduction to mass transfer. Okay, done. So why you need to understand mass transfer? Why is mass transfer is so important? Why you need to understand mass transfer? So this is important for you to know. Okay, so I will brief about this. So I give you an example. Okay, separation of solid from liquids. How can you separate a solid from liquid? Anyone know the answer?
Pakai
Okay,
tapis.
yeah,
Filtering.
filtration.
Filter.
Okay, thanks for feedback. Filtration or centrifugation. Okay, second. How can you separate two liquid mixing which are completely uh, immiscible? What is immiscible? Immiscible means it will not form a homogeneous mixture. Not form a homogeneous mixture. Okay, to make you understand, for example, you have a beaker, so you have component A and B, so it will form two layers. It means that it is not form a homogeneous mixture. If homogeneous, A and B together in the solution in one layer. Okay. So how can you separate two liquid which are completely immiscible? So you can use decantation. So the concept of decantation is like this. So you separate A and B by density difference. Okay. But how if I ask you how can you separate a gas from a liquid? How can you separate gas from a liquid? Or how can you separate uh, two miscible liquid? Okay, this one is immiscible. Immiscible may not form a homogeneous. If I said miscible, mean it is homogeneous. So if this one you can separate it because it form two layer, but this one is one layer. So because of this, for example, this one is just example for you to think. So that because of this, that's why you need to understand mass transfer operation. Okay. Next, okay, this is the example of mass transfer, evaporation, and this one we have a sugar in a water solution. Then the sugar, then there will be a mass transfer in this container. Then it will become sugar solution. Dissolving of sugar in water is one example of mass transfer. Okay, so we move on to diffusion. Okay, what is diffusion? Diffuse means species A, for example, will move from a region of high concentration to the region of low concentration. So from one point to second point, high concentration to low concentration. Okay, for example, you have an orange molecule. This one is diffusion of one solute, and this one is diffusion of two solute. So you have a molecule of dye. So after certain time, the molecule from high concentration will move to low concentration. So then you can get the equilibrium solution. Same concept for this one, where you can see the yellow molecule and purple molecule. Then after a while, there is equilibrium of both molecules. Okay. Okay. I think this is a simple illustration for you to understand what is diffusion. As you can see, when we drop the crystal violet, or simple I say purple dye, so then it will diffuse in the solution slowly and slowly, then it will become purple solution. So that is what we call as diffusion. So another example is, let's say in one room, I spray a perfume. I spray a perfume in this room, yet soon the perfume will diffuse so that you can smell it anywhere in the room. Okay. So we move on with Fick's law and molecular diffusion. Okay. Okay, what is molecular diffusion? Molecular diffusion. So of course it is a transfer or movement. There must be a transfer or movement so that mass transfer will occur. Okay, transfer or movement of individual molecule through a fluid. When I say fluid consists of what? Fluid consists of gas and liquid. Okay, individual molecule through a fluid by means of random individual movement. Means it will move in random movement. Okay. Then the Fick's law will apply when the whole bulk fluid is not moving. It means that only the, as you can see, only the purple solute that is moving, not the whole of the solution. And diffusion of the molecule is, of course, must have concentration gradient. Concentration gradient means concentration different. Okay. Okay, so Fick's law is applied in fluid. Fluid consists of liquid and gas. Okay, what's Fick's law all about? Okay, Fick's law. This is the general equation where we denote as J as Z is the molar flux. Molar flux of component A in the Z direction. So this one, component A in Z direction. Okay, hope you understand. Okay, C. What is C? C is total concentration. This one. Okay, what is DAB? DAB is the molecular diffusivity of molecule A in B. Molecule A in B. That's why AB here. Alright. So, DXA. What is XA? XA is mole fraction of A. Mole fraction of A. Okay, for example, in a solution, you have A and B. So you must know the fraction of A how much, the fraction of B how much. Okay. So if you want to know the concentration of A, for example, so you must multiply the mass fraction with the total concentration, Ca. If you want Cp, Xb times with C total. Alright. Okay, dz. Okay, dz is the distance of diffusion. As you can see, this one is 0.1, this one is 0.2. So we have z1, z2. So this is the distance of diffusion, right? So this one is the molar flux. Molar flux from location 1 to location 2. Right? Okay. I think it's clear.
Medium saya tak faham.
Which one you don't understand?
Medium, yang JAZ tu, like, can you repeat the explanation?
Yes, that one.
Oh, what is A and what is Z, right?
Yes.
Yeah.
Oh, okay, it's okay, I can explain. Okay, J, A, Z. What A and Z stand for? Okay, as this one, it's written here, molar flux of component A. Molar flux of component A. In the Z direction. Z is the direction of the mass transfer. We will have 2 points, so it shows there is a transfer. Okay. So Z is the distance of diffusion. Molar flux of component A in Z direction. Actually, it's just a notation. So I just explain what is exact. This one. Nothing to be worried, I think, with the exact. Okay. Okay. Okay, Fick's law for steady state diffusion of a binary mixture of A and B. Okay, this one is the general equation, sorry. So we integrate the dCA and dZ, so we will get the final equation for liquid. Okay. Then for gas, we will apply ideal gas law. ideal gas law where PV is equal to nRT. Then P over RT is equal to mole over volume. Mole over volume is what? Concentration. So you should know this equation. Concentration is equal to mole per volume. Okay, so you will get this equation for PA1 over RT is equal to CA1. So you substitute into the equation. Equation for liquid is Ca2, Ca1, Z2, Z1. But for gas, we are using pressure, right? So you change with PA1 minus PA2 over RT. So you will get this equation for gas. Okay, maybe because you first time learn, so maybe you cannot absorb all for this time. So that's important for you all to revise back and study back this one. Actually, it is not so tough. When you revise back, you can clearly say this one. Just you substitute back the concentration. Then you use for gas, so we must use the ideal gas law. Okay, so maybe you have to done this example so that you can see it. Okay, we see example 6.11. After this, you all have other class or what? It's already 2:35. Okay, so okay, I make it faster. So we have a mixture of helium and nitrogen. So stated here is a gas. So we must use the gas equation. Helium and nitrogen gas is contained in a pipe at 298 Kelvin. So this one is the temperature and 1 atm total pressure. So P total, which constant throughout. At the end of the pipe at point 1, the partial pressure is given. PA1 is 0.6 and at the other end 0.2 meter. Other end, so this one means Z2. PA2 is 0.2 atm. Calculate the flux of helium at steady state. Then DAB is given 0.67 and the gas constant also given here. So you use back this equation for gas. Okay, so JZ is equal to DAB PA1 minus PA2 divided by Z2 minus Z1 RT. Okay, DAB is given, so just bring back 0.6 at 7 times 10 negative 4. PA1 is given, right? 0.6. PA2 0.2. Okay, Z2 is 0.2. So Z1 of course 0. Okay, Z1, Z2. It's stated here at the other end is 0.2 meter. So of course it will start with 0 meter. Okay, so R is given here 82.06 times 10 negative 3. T 298. So later if you have a calculator, you can calculate this answer. You should get the answer 5.63 then -6. Okay, this is a simple example for you to understand and apply this equation to solve this problem. You are calculating the flux. Okay. Okay, I think you should take a break about 5 minutes before we continue back. You all have class after this?
No.
No, we have class on 5.
Oh, okay. But it's okay, I try to finish by 3 p.m, okay? So you all
Then
can rest for 5 minutes, maybe want to go to toilet or what.
Medium.
Ya, Nafal, Syakir Nafal.
Can you open the slide before this?
Okay, which slide?
Slide 17 tu. Slide
7.
17. 17.
7.
Yang example tu.
Okay.
Okay, thank you Adam.
Okay, it's okay.
Adam.
Okay, who's talking?
Saya.
Okay, Sharif.
Hello.
Yeah, Sharif, I'm here.
Yang equation yang tadi kan liquid gas tu, dekat liquid DAB tu negatif, tapi dekat gas dia tak negatif.
Oh, actually this one it's just the same, but can you notice for liquid is from A2 to A1. Okay, but for gas is from A1 to A2. Actually, negative sign is just to denote the direction of the movement. For example, okay, A1 to A2. Okay, A1 to A2. This one is, oops, sorry. This one is A2 to A1. A2 to A1. This one is from A1 to A2. It's actually it's just the negative is just want to say the different of direction. This one from A2 to A1, so if we do A1 to A2, so it will become negative. Later in equimolar, I will explain more to you about that. Yeah, we will have negative sign. Okay. Okay, we start back our class. Okay, we're done with this example. So we move on to diffusion through stagnant film and equimolar counter diffusion. So I will cover this one only for this class. Okay, equimolar counter diffusion. Equimolar. When you say equi is actually equilibrium. Equilibrium means the movement is the movement of A to B, for example, and B to A must be equal. Okay, for example, you have yellow solid we denote as A and the purple solid we denote as B. So we can see there is only yellow solid in this section and there is purple solid in this section. So after a while, there is a combination of A and B in this solution. So for this one, for you to understand, I will draw some of the diagram. Okay. Okay, so this one you will have PA1, PB1, PA1 plus PB1 is equal to total pressure. This one you will have PA2, PB2. So it's the same, PA2 plus PB2 is equal to total pressure. From point 1 to point 2, so there will be a movement of A. A from point 1 to point 2. Okay. B from point 2 to point 1. Okay. Then JAZ will equal to negative JBZ. Why negative sign I put here? Negative sign is just we want to denote JA, flux of A happen from point 1 to point 2, while flux of B from point 2 to point 1. It's just to denote the different direction actually. Okay. Later when you all done your tutorial and a lot of exercises, so you will understand more about this. Okay. Alright.
But the value still in positive.
What?
The value kan Madam said is just a donut or the different direction, right? But then the value still will be in positive, not value.
If the question asks you to find JZ, this one positive. If the question asks you to calculate JBZ, you have to put negative sign. Later we will done an example after this to find JZ and JBZ.
Okay, Madam.
Okay, so another diagram I want to show. Okay, for example, this one. Okay, you will have PA1 here, PA2 here, then PB1 here, PB2. Okay, so PA1 should be greater than PB1. So molecule A will be transferred from this point to this one. For this one, PB2 must be equal to PB1. Okay. Okay, you can read first this question. Actually, the question is just the same like example before this. Just you have to find two flux for A and B. Okay. Okay. Okay, ammonia gas. You have ammonia gas. A is diffusing through a uniform tube of 0.1 meter long containing nitrogen gas as B at 1.0132 Pascal pressure, temperature 298. At point 1, PA1 is given, and at point 2, PA2 is given. The diffusivity DAB is also given. Then you are asked to calculate the flux of JA and JB. So it's stated here is a gas. So we take the gas equation before this. So first we calculate JA is equal to DAB PA1 minus PA2 divided by RT Z2 minus Z1. Okay, DAB is given, right? 0.230 times 10 negative 4. PA1 is also given here, 1.013 minus PA2. PA2 is 0.5. 10 to the power of 4 divided by R is given here 8314. Temperature also given 298. Then Z. It's stated here 0.1 meter long. So 0.1 meter 0. So this one is Z1, Z2. So 0.1 minus 0. So you will get flux of A 4.70 times 10 negative 7. This one. Okay. For JB, you will also use the same equation, but this one is for A, so A1, A2. For B, you substitute with B1 and B2. Okay, divided by RT Z2 minus Z1. Okay, the problem here is you don't have PB1 and PB2. So, how can you find PB1 and PB2? Okay. PB1 is equal to P total minus PA1. Okay. Maybe you cannot clearly see, so I move back to this slide. Okay. You want to know PB1, right? And PB2. Okay, it's given here PA1 plus PB1 is the total of P. So if you want to find PB1, then just P minus PA1. Then if you want to find PB2, just P minus PA2. Okay, move back to this question. So PB1 equal to P minus PA1. P total is given here, okay? So 1.0132 minus this PA1. PA1 is given, right? Okay, 1.013 times 10 raised to 4. Then you will get PB1 9.119 and okay. Next, the same you find for PB2 is equal to P minus PA2. Okay, so P total 1.132 minus PA2. So PA2 is here. 0.507 times 10 to the power of 4. So you will get PA2 9.625. Okay. Oh, sorry. Okay, so we put it back in this equation. So G will equal to, what is the AB? Okay, 0.230 times 10 negative 4. Okay, PB1 we have find, right, 9.991. Okay. Sorry, we must minus this. Minus this PB2, 9.625, 10 to the power of 4. Okay, divided by R is given the gas constant of 8394. T is 298 Kelvin. Z2 is 0.1 minus 0. Okay. So you will get 4.7 times 10 to 7. So for this one is question that you asked before. Where have I to put the negative sign in the calculation? Yes. For this one, JA is positive, then JB is negative. To denote that A is moving from point 1 to point 2 and B is moving from point 2 to point 1. Okay.
So the final answer, then we should put the negative sign.
Yes, correct. You should put negative sign. Okay, I think that's all for our class today. It's already 3 p.m. So I will put this slide in the file in Microsoft Teams so you all can revise back so that you can understand more on this. Okay? Okay, everyone? If you have any question, please do not hesitate to ask me. You can just use Telegram, WhatsApp or whatsoever. Inshallah, I will try my best to entertain and answer your question. Okay?
Okay, madam.
Okay, madam.
Okay, madam.
Okay, madam.
Yeah. Thank you.
Okay.
Oh, sorry.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you,
madam.
So how do you feel for this class today?
Madam.
I feel great.
I feel great. Okay. Okay then. Okay then. Thank you all. Have a nice day. Assalamualaikum.
Okay,
Thank you,
madam.
madam.
Salam.
Salam.
Madam.
Have a nice day too.
Thank you, madam.
Have a nice day, madam.
Thank you, madam.
Thank you, madam.
Welcome.